Here we're going to consider what solution curves look like without actually finding any solutions. If y equals y of x is a differentiable function, then we know that dy dx gives the slope of a tangent line at a point. So if we have a differential equation, dy dx defined as a function of x and y, then for any point x and y, we know the slope. Using little segments of the tangent lines, called lineal elements, we can generate what's called a slope field or a direction field. And this is what a direction field looks like. The differential equation in question here is dy dx equals x squared minus y squared. And at any point xy, we can find the slope of a tangent line, and the picture here of all these little arrows provides little pieces of tangent lines at any particular point. Our task is, given an initial condition like y of -2 equals 1, figure out what the curve looks like that goes through that point. Well, the first thing we're going to do is plot -2, 1. And then that little segment that I put that dot on is a slope of a tangent line, and so right there the tangent line would be going up, looks like at about a 60-degree angle. But then as we go up, the slope of the tangent line starts changing, and you can kind of see what a curve would look like if it had these little segments as its tangent line at each point. And I kind of think of it as if you were in some sort of body of water, and this was the current, where would that current end up taking you? So that curve here seems to obey the little tangent line segments, but we can also consider what would be an appropriate curve going to the left here, and it seems like this is going to come from down here, maybe going that way. These are approximations, of course. That's for the initial condition y of -2 equals 1. I'd like you to pause the screen for a moment here and try to see if you can come up with what it would look like if we started at the point 3, 0. All right, I hope you paused it. 3, 0 is right here. It looks like this is going to take us pretty much straight up and then up in here to the corner. And then it would have come from maybe down here. So I'm just kind of working backwards. And it looks like it might come from about the same place that the blue one came from. Let's do the same thing with the initial condition 0, 2. So you're looking for 0, 2, and then try to visualize what this curve would look like. I'll draw it in just a moment. 0, 2 is here. It looks like we're going to sweep down and then quickly go up here. And then that's going to come from kind of above there. And I'm trying real hard not to make these curves actually overlap, because remember, we can only have one solution that goes through a particular point. So that's 0, 2. And then for the initial condition 0, 0, we're looking at the curve that goes through the origin here. Looks like it's kind of flat there. Again, coming from down here. Can I squeeze it in there? And then maybe dips down and goes up here. And I'll just stick it up here in the corner. And folks, that's what curves look like for this slope field and these initial conditions. Next, we're asked to use computer software to get a direction field. And I'll tell you, you're not going to be asked, at least by me, to produce a direction field by hand. Our differential equation is y prime equals x plus y. And what I've done is just gone to Google and searched slope field generator. I'm looking here, I see one from Desmos, I see one from GeoGebra. I'm going to use the GeoGebra one here. Thanks Chip Rawlinson for making this. It'll always default with the same function, but we can retype to give us y prime equals x plus y, and there's our slope field. And I'll just go ahead and paste that into our current working document. And then it's the same thing we just did. y of negative 2 equals 2, so I'm going to be looking for the point negative 2, 2. And then drawing a slope, a solution curve that looks like it could have these things as its lineal elements, as its tangent lines, I should say. We'll just finish this up looking at the initial condition 1, negative 3. And again, to be really clear, that means we're looking for a curve that goes through the point 1, negative 3. That's what an initial condition is, a point on the solution curve. I see here the y-axis is marked negative 2 and negative 4, so I kind of did my best here. And then that looks like it would come from maybe up here. And in the same area as where the orange one comes from, but this one's going to sweep down here. Not very exciting, but you can see some trends here. And what I notice here is from the upper left, they seem to be pretty close together, but the first one diverges from the second one. It goes up to the positive y-axis pretty quickly here. The green one ends up crossing the negative y-axis and then going down to negative infinity. So a slight difference way over here on the left leads to a pretty big difference over here on the right. We're going to contrast that with the previous one. And 3 of them start in the lower left, the quadrant 3, and end up in the upper right, quadrant 1. The difference here is what they experience in the interim. But you can see that a lot of solutions are going to generally go from the third quadrant to the first quadrant with kind of a wiggle in the middle. And then we can also see a solution from the second quadrant is going to swoop up and end up in the first quadrant. And it seems that unless we're down here on the negative y-axis to end up going down into the fourth quadrant, most of these solutions that we're looking at would go up into the first quadrant. So you can kind of see a general picture of what a differential equation is telling us.